techniques. All those techniques of integration is behind us now. So during class, I might ask you or remind you how to integrate by parts or how to do partial fractions or things like that. But we're not going to drill too much of those Calc 2 stuff. Although when you go to differential equations, those integrals should come secondhand to you. So between now and when you have to take differential equations, if you haven't already, you should see if you can tutor Calc 2 so you can remind yourselves of how to do that. The focus more is on the theoretical aspect of trying to integrate things and the geometry of what these integrals actually mean. And so this is an extension of something that we've studied before. So the first thing to probably look at is to look at what we have studied before. And what did we study before? We studied integrals where it's over 2. Yep. The first application that we've had for integrals are looking for area under the curve. And when you look for an area under the curve, when we first started to do integrals, it's hard to find areas of under the curve where the curve is not, just a straight line. Because if the curve was a straight line, then we can find the exact area using triangles and trapezoids and things like that. And so when we started looking at things where the curve is curved, we have to do estimates. And so this exercise of finding rectangles, where finding an area of rectangle is easy, it's just base times height, and then shrinking the rectangles to infinitesimally small base and adding up an infinite number of rectangles changes our adding these rectangles, which is our Riemann sum. It changes our Riemann sum into a definite integral. Yeah.
So
the integral technically is an infinite sum. Yeah. So that's the sum that goes from the sigma notation sum to the integral notation sum. So back in Calc 1, or I guess we did a little bit of this in Calc 1, but most of this kind of fell under Calculus 2. We have y is equal to f of x, some function, and then we started off by taking partitions of your interval. And so our interval is a nice one-dimensional interval because our function f goes from R to R. Our domain is one-dimensional. So we take our input from our domain as a one-dimensional interval, and then we take our interval and then we partition it with x sub i's. And we let the first and last endpoints of our partition to be the endpoints of our interval a and b. And so we do this partition. And then technically and generally, you can have any size length for your partitions, but for the sake of what we want to do, we have the size of our partitions, the size of our subintervals to be all the same, just to make things nice and easy for us. And so the size of our interval would be depending on how many partitions. In this case, we partition it to n different partitions. The size of our interval we denote as delta x, and delta x is going to be essentially the length of the original interval, and then we divide it evenly into n partitions. And so that becomes our delta x, and that becomes our base of the rectangles. And then now comes the question of the height of the rectangles, and it turns out that within each subinterval you're free to choose what you want your height to be. You can choose the left endpoint and the right endpoint, and hence we have those left and right endpoint methods, and you can choose a midpoint, but you can be as random as you want. You can choose any number as long as you're between your subinterval, then any of those would work. But it turns out that regardless of what you choose, if you're going to take the limit as the n gets larger and you have more partitions and the lengths of those subintervals get smaller, then it's all going to amount to be the same thing. So it doesn't really matter which one you choose. So the height then is going to be the function evaluated at some point within some subinterval where x sub I star is an element. This is an E element of the closed interval x sub I minus 1, the ith interval basically. And so base times height, so this times delta x is your rectangle. This is one rectangle, and you add up all those rectangles. Then you have an approximation, and usually the larger your n is, the better the approximation is until you take it all the way to infinity. And this is where your Riemann sum, this is your Riemann sum here, becomes your integral. And that's the definition. Yeah?
What does it stand the limit?
N goes to infinity. Or sometimes, because as n goes to infinity, then the size of the delta x's gets really small. So another way to describe this, and this is all equivalent, you could say the delta x equals 0. Or all those sizes are different. Sometimes they call it a partition or the mesh. And so the mesh goes to 0 is the same thing. So this integral sign is actually a fancy S for sum. Sexy looking S. Yeah. I told you about my little tattoo dream, right? It's going to be a tattoo of the integral sign right on my leg. Never happened. Well, I had it on permanent marker one time. It was cool. I just put permanent marker on it like every week, and then you can say I have a tattoo of an integral sign. All right, so that's a story. It's a nice story, bedtime story. Tell your kids. Tell your kids about the integral. Or friends, or if you don't have any kids. Your nephews. Okay, so now if we think about extending this to our new types of functions that we're dealing with, how can this be extended? Before we take a look at any pictures, let's think about how to extend this to these types of functions where our function now has an input of R2 and an output to R. Z is equal to f of xy. So we got some fundamental difference now between the old function and the new functions, and then in that your new function that you're dealing with has a different domain. And you look at the domain for our old function, our domain is just a number line x, and then so our interval, there's really not much choice to integrate, and we can integrate from A to B, or we can integrate from A to C and then integrate from C to B, and then, you know, it's still, there's not much freedom in how you can set up your domain and your limits of integration. But now when we're talking about R2, that's a totally different story. We had issues with this when we talked about limits. You know, we're limit at a point. If we had a number line for our domain, we go from left, what? We go from left to find the limit from the left, find the limit from the right, and see if it worked out. So that was easy. And now when we take limits, when our domain is more complicated, we have an infinite number of paths to get there, so that became a lot more difficult. The first derivative test, we just talked about that this week. The first derivative test, it's also easy to look at because you go from the left, you go up, and then you go down past your critical point, you go down. So again, examining your movement along your domain in one dimension is easy. But we found out that we can't use the first derivative test for these types of functions, so we have to come up with a second derivative test, where we had to get the second derivative involved and take a look at the concavities. So there's a fundamental difference between our old functions and our new function, where our domain is now in R2. So if we were to integrate this, if we were to go back to take a look at our discussion, we have a function on an interval. How would we rephrase this when we're talking about this function now? So this function on what? What do we need to do to describe some sort of... Is R2 a surface? It's on the plane, and we could be exact. We could be exact on an actual plane. So this is the plane, xy. So your domain is now going to be in xy. And if we want this, if we want for us to make sense out of this, our domain should be a two-dimensional region, because our input values are coming from 2D. So on a 2D region on the plane. Okay? Sometimes we call it R or D. R for region or D for domain. And in our previous discussion, when we found this integral, we were actually looking for the area under the curve, right? And this is your curve. We have a curve. We have a base for the curve, your interval, and then we found the area under there. So now if we're taking a look at this as something that's happening here, let's say this is our R, your region, and this is your... It's not a curve anymore, it's a surface. What are we essentially looking for geometrically here? Space under the surface. So if this is our region R, that's on the xy plane, it's on the domain, that's where your input's coming from, then we can imagine taking a look at this thing being projected up, and then we have a space here that we're trying to find. So in terms of geometry, this would be called a volume. Brian?
That region is just occupying.
Yeah, it's occupying a two-dimensional, something on the XY plane.
Right.
Yeah.
So no height.
No height.
Okay.
So this is a two-dimensional region. 2D region on the XY plane. Okay. So that's kind of interesting, and that seems like it's a natural generalization. You got something that's two-dimensional, and then that will end up being your base. And then now we just multiply it by the height. Okay. So the next part of the story is the partition. So we have an interval. That's the easy one-dimensional interval from A to B, and we just cut it into little partitions so we have little subintervals. Now imagine trying to do something like that to our region here, because that's our base. So so let's take a look at our region, just flat region, just like we kind of take a look at the number line as a flat number line. Let's look at the region as a flat region. And this is our region. Look at the blue. So we need the idea of a partition. We want to be able to partition this, right? And so, again, with a number line, partition just means, oh, we just cut it up into equal parts. But here, cutting it up into equal parts might not be so easy. And so what they do is they backtrack a little bit and say, okay, instead of looking at any random region, why don't we take a look at a square region first, or a rectangular region first, you see, and make that a little bit easier to deal with, and then we'll try to extend our ideas to the rounder and more stranger looking regions. How is this going to help us partition?
So you can do like little squares.
No, maybe we could do little squares, right? So if we just cut this up into little squares, that could be like one of this randomly chosen little square over here could be our yeah, something like that. So let's go back to our three-dimensional picture. Now let's incorporate this idea that we changed our mind and went to a square region instead, or rectangular region. And then we cut that up into little partitions. And we shaded one of them over here. So if I just want to focus on that one, and that would be my base, and then I can randomly choose some sort of height over here where I can pick any point. Could be one of the endpoints, could be the midpoint, right? And then I designate that to be the height of my rectangular box. I guess it's a box now. Then I can find my volume. And then just imagine if I add up a whole bunch of those. All right, so how's a partition going to go? We're still back to the idea of a partition. Now, instead of just a partition along the x, I have a partition with the x and the y. And so, well, let's just partition it along the x and the y. So our x goes from like maybe A to B. A y goes maybe from C to D. And so we can partition x with x sub 0, x sub 1, x sub 2, all the way to x sub n like we did before. And then, well, it kind of makes sense to partition the next one from y sub 0, y sub 1, y sub 2, all the way to y sub. It doesn't have to be the same n. It could be, I guess, but it doesn't have to be. Let's call it m. And then we could take a look at this as the ith position, x sub I minus 1 and x sub I, and we can take a look at this as the jth position, y sub j. And then, so each of these boxes in 2 dimensions would be box 0, 0, box 1, 0, box 2, 0, and so this would be the box x sub I, y sub j. Let's just call it r sub ij. Right? So to find the volume geometrically, volume is usually length, width, and height all multiplied together. So I'm interested now in finding the lengths of these sides, and then the height is just going to be the function evaluated at that. So maybe we can think about partitioning this just like the way we partitioned it, with equal lengths, with n of them. We probably call it delta x, right? Delta x equals b minus a over n. So that's our delta x. Actually, this is not going to be important for us, but we can just say that that's what we chose to be your delta x. And then your delta y would be the distance along the y, which could be d minus c over m. But the point is that the area of your r sub ij is actually now just equal to delta x times delta y. So now we have 2 deltas, delta x and delta y. Last time we had 1 delta. And I didn't make a big deal out of this last time, but when we come to the limit, delta x would become your differential operator dx. So with a delta x, delta y, that's probably going to become a pair of differentials, dx, dy. All right, so we got the area of the base, and now we just want the height. So base times height business is the same thing. And if you take an I, x sub I, and y sub j point on your domain and put that into the function, that's going to be your height. So that's it. Well, right? That's it. So the volume of this one single pillar could be seen as f of x sub I, comma y sub j, delta x, delta y. And now we take that and then add up along the x and along the y. So this is going to be a double sum. So we take your height times delta x times delta y, and then now we add up along the x's or along the y's, and then we add up along the x's. Okay. And then if we throw in a limit as m and n go to infinity, number of those partitions get large, each of these sums would now become an integral. So limit as n goes off to infinity and m goes off to infinity. We could kind of think about doing it separately, but it's better to think about it as having the same, it's all kind of interwoven. And then now this is where you get your big prize formula. So the function, you lose the i's and j's because you're just assuming that they're going to get infinitely small and just going to come to that one point. The deltas will become a dx and then dy, and then one limit for your y value, or actually this is going to be your x value first, so this is going to go from a to b, and then this is your y limits going from c to d. So here we have what's called a double integral. And that's it. That's your double integral. Generically, double integrals can be written like this, where you have a double integral over r of your function dA, where a is your change in area, so to speak. And so it has to be understood that the dA is actually a pair that goes into dx and dy. And I keep saying dx and dy, but realistically, it could be dy and dx, and it depends on how things are broken up. We'll see later on that your domain is going to play a big part in how you're going to be able to set up your integral. Sometimes people tend to use just a single integral to represent this. So if I ever use a single integral, but I use r or d, and then I have some function here and I have dA, then you should know that this is actually, in fact, a double integral, because the dA represents the dx dy combination. Okay?
But when you put on one integral, what does it mean that the x and y is going from one point to the other point to the same for x and y?
What do you mean when I do a single integral?
Yeah.
Yeah, when I do a single integral, it's understood that when you actually start to work it out and write out the integral for you to try to compute it, then you'll eventually make it into a double integral.
But from the same point, like if the a to b is going to be the same as c to b?
Not necessarily. Yeah. In fact, for a rectangular region, you will be using A, B, C, D, and stuff like that. But if it's not rectangular, then you'll see that the way we set up limits is going to be a little bit different. Okay? All right, so for what it's worth, I have some pictures that I can show you of this theory. I guess this should be finding volume, but anyways. Oh, this is just a code. I didn't make it into a nice little change parameter things. So I took the saddle as the function and I moved it up a little bit so you can see. And this is the crude approximation of 4 partitioning my interval. I think it's going from -1 to +1, and I just break that interval up into 4 equal parts along the x and along the y. And so the graph would look something like this. And these are boxes that go up that measure the height of the volume that I'm trying to compute. So I can change that into where am I going to change it? Oh, it goes from -2 to 2, and our delta x is 4, and our delta y is 4. So can you guys see this picture? I keep looking at it from this side. I can't see what you see. You see an angle. I see it really clearly on my screen, but I don't know what you guys see. So anyways, as an example, this is how it might look like.
Is this the same as like 2D integrals where you, if you go below your x-y axis, it will become negative?
Yeah. I think this, yeah, so in this particular example, everything is positive, so it looks a little bit nicer. I have a +4. And then my domain or region is x and y, so between -2. So this is with 4 partitions. Let's take a look at this picture, but instead of partitioning the n into 4, let's partition the y's into 4 pieces. Let's partition the y's into 8 pieces. And we can see that it's not square anymore. And we still get some sort of approximation to that, right? So you can tell the difference between these two things. So this first picture is a picture where delta x, or I'm sorry, n equals 4, and m is equal to 4. And I think this one, n is equal to 4, and then m is equal to 8. That's the number of partitions we choose. And so if I didn't actually have it compute the volume, but if we actually have this go up to like 20 or something, then I should have a pretty good approximation. Just like its counterparts back in Calc 2, where the more partitions you get, the better your graph's going to look like, or the better your approximation is going to look like. What was it again, 20? Okay. So let's actually do one quick calculation before we try to extend our ideas to more complicated things. No, I guess before we do a calculation, I have to do some numerical examples first, because I think you have some of those in your homework. Here's a numerical example. This is from your, no, I don't think this is, I think this is from another textbook, because it says 12.1, and you guys have, we're on chapter 15 now. All right, so let's do this example where you have a table that looks like this. So these numbers over here is, I asked you what C of 40 comma 3.5 means. This is the cost. That you would try to sell your beef, cost per pound, I guess. Of how you're going to try to sell your beef based on your income and the price that you bought the beef for. All right, so what's all this stuff? So this is I guess this is the visual representation of those values that you have given a certain amount of income and things like that. income and the price of the beef. And then I guess we should label the axes. This axis over here looks like it's the income level. And this axis over here looks like it's the price. And the height over here is the cost. So let's say we're interested in integrating this cost function with respect to what variables are we going to use? B and I as a function of the income and the price of the beef, and then delta A, I'll say delta A now. And let's say we want to integrate over this whole thing. Well, what does that mean when you integrate over that whole thing? You have cost in beef. Well, it turns out one of the applications for the integral, you guys remember what the average value is?
Yeah. There's 1 minus b, 1 over b minus a times the integral of f b by a, of whatever.
So what we could do, I guess what I was trying to do here is so the average value is what AJ said. let me backtrack a little bit and remind you what the average value is. Average value is of F over AB, and this is sometimes denoted as this, AB over F, and this is 1 over B minus A integral from A to B of F dx. So what does this mean? It means a couple of things geometrically. It's the average. If you have a function, it looks like this from A to B. The B minus A is this length over here, right? It's the length of the base of what you're integrating over. And then if you get this average value equal to, you will eventually get this average value to equal to a number, or I'm sorry, the integral here. Yeah, let's just scratch all that out. The integral here, let's say this integral is equal to a number, and we'll call that number C. That number C is going to be the average y value of the function. So it has to be somewhere over there. Okay? And the average value would be, it should be somewhere, you know, within your interval, or some representative that would represent the heights of your function. Geometrically, what this means is that if you draw a rectangle that has a height C, then the area of this rectangle is going to be the same as the area under that curve. Does that make sense? So if we take this equation over here, it says the average of A and B of F, and let's multiply this on both sides by B minus A is equal to C, or is equal to the integral then that's essentially saying that this is your rectangle here. This average value for that function is a constant, which is your rectangle, times the base. So this is the height times the base. That would equal to this, exactly equal to this thing, this integral. Okay. So if we think about that as one of our first applications for our double integral, we can take a look at and define an average value over a region. So the average value of this thing would be, we can think about this as an application. That's the average value when your income goes between 20 to 100,000, and the price of the beef goes from $3 to $4.50, and what's going to be your average value over that domain. Okay. So the average value is going to be given by not just this double integral, but we also have to, divide out by the area of your domain. Does that make sense? I don't think I was supposed to talk about average values until like a couple of sections from now. But I kind of wanted to make a point about why we would bother integrating over this thing. So we would want to integrate over this so we can find the average value of the beef as your income and the price of the beef changes. Okay, so there's going to be several ways. Since these are discrete numbers, they're not continuous, we're not going to get an exact value with this thing. So for us to be able to compute this, the best we can do is we can find averages, or not averages, but approximations. Okay, so what we have to imagine is that we go back to a ID grid. So let me start off on the new page here. Your I grid, let me change my axis since we're all positive. Your I grid and your B grid, and your I goes from 20 to 100, and then your B goes from, what is it, $3? $2? $3 to $4.50. And with these discrete points, we have a natural partition. This goes by 20, and this goes by 50 cents. 20, 40, 60, 80, 100, 3, 350, 4, 450. So at each of these points, what was that first question that they asked? 40, 350. 40, 350 is this point over here, and that has a C value that has a C value 40, 350 is 405. Okay. So this is how we would get these heights now. So each of these things would be your base for the rectangle, and then the heights would be given by those C's. Now the thing is that when you pick a rectangle, it's up to you on which point, because remember, you have the freedom to pick any point that you want. So if I'm looking at this rectangle over here, I can decide to pick whichever point I want as long as it's within that rectangle. Okay, so let's say for each rectangle, I'll pick the upper right-hand point. So for this rectangle, I will be picking this point. So the volume of this rectangle, let's call this R11. So the volume of this rectangle is going to be the base, or the length, I guess. 40 minus 20, that's 20, times the length times the width, 50 cents, times the height. And if I'm choosing this to be my height is going to be 4.05. So that's for my one rectangle. Let's randomly pick another one. So upper right-hand corner, right? We want to pick our upper right-hand corner. So this would be your rectangle 1, 2, 3, your rectangle 3, and then 2. And this has a base, well, the length and width will be the same, right? Because this thing is all partitioned evenly. But just in case you want to double check, this is 60 and 80. 80 minus 60 is 20. And then this, $4 minus $3.50 is 50 cents again. And then now the height is the cost at 80 and $4. So we need to figure this out from the table. 80 and $4 is $5.19. So that's the volume for the rectangle 3, 2 or 3, 2. Okay? So if you want this double integral of the cost function as a function of I and B, where you integrate with respect to I, you're going to go from 20 to 100. And then you integrate with respect to B, you're going to go from 3 to 450. Then you're not going to be able to figure this out because it's not a continuous function, but you can certainly approximate with just adding up a bunch of these rectangles. So it's the cost function at some points, and then again, it depends on whether you take the upper right-hand points, upper left-hand points, or lower right or left-hand points. There's no points in the middle because the table doesn't give that information. But I'll put stars here to say these are some points that you would selectively choose. And then your delta I and your delta B are the changes in I and changes in B. And this is where you're, along the I, you're going to go 1, 2, 3, 4. I'll just put 1 to 4 here. I don't have a variable here. And then your B goes from 3 to 450, but it only has 3 partitions. So 1 to 3. So you'll probably be adding up 12 rectangles here that you'll have to do by hand. And delta I is 20. The delta B is 50 cents. And then these things would be just numbers in the table that you would collect. And then you would just add up 12 numbers. Yeah?
You want to find average value, you just divide that by 100 minus 20 times 450 minus 3.
Yeah, you divide that by the area of the base. So this is the actual integral, and then yeah, to find the average value has this added. You're dividing by the base business, so. Yeah. Okay, does a numerical example make sense? Okay, so remember to transfer this information, this table information, mainly the places, the tick marks for the x and the y, transfer that onto an xy plane or a flat plane, and then you can figure out how your rectangle is going to shape up that way. And then from here, depending on what the instructions are, that they tell you to use the upper right-hand corner or lower left-hand corner or whatever, you just need to figure out which points to use for each of the partitions that you make. Yeah?
Are there Riemann sum calculators that we can use to just put in a table and then those? Because there are, I know, for 1D, but...
Where you put in the table?
No, just one dimension where you're like,
Oh.
this is my function, put it into like
Yeah.
5 partitions or whatever.
Yeah, for this one, you physically have to put in the table, so physically putting in the table is almost the same thing as computing it yourself. Because look at what you have to do. This is going to be a constant all the way through, right? So when you're adding this up, the delta I and delta B, you can multiply. This would be 10 in this case. I could just factor that out. So what am I really adding up? I'm really adding up all these numbers, and then I'm multiplying it by 10. So that's putting that into a calculator is almost the same as putting that into an Excel file and pressing sum and then multiplying it by 10. The same thing. So if somebody wrote one of those up, then it's probably a really simple program to write. And if you can code in any language, Python, maybe you can make one up and share it with the class. Or give it to AJ since she wants. Yeah. Yeah, because that's how many rectangles along the x and how many rectangles along the y I'm counting. This is like your m and your n from how we defined our partitions before. All right, let's see. That's it. The more interesting business here is when we actually start to compute it. So let me go back to our example over here, and how can we expect to compute this? What's our example? Our example is a function, the saddle, and our domain or region is the set of points from -2 to 2. So we saw a picture of that, right? So let's jump to actually computing this. And the way we compute this is that we'll write it out like this. Well, I can write it out several ways. Let me first write it out as an integral of the function dA. And now let me write it as an actual integral that we're going to be able to compute. So f of xy, well, let me just put in the actual function here. X squared minus y squared dx dy. And now I have to remember that since I put my dx in first, we're going to calculate this as if it's called an iterated integral. So the x values are going to go from -2 to 2. In this case, they're going in the same limits, but it'd be more interesting if they were going different limits. The y is also going to go from -2 to 2. So the way iterated integrals work is that we're going to integrate from the inside going out. So what that means is that when we do this integral, we're going to look inside, and by inside, I mean it's that first d that you run into when you go at the end with the differentials. And then integrate this with respect to x first, and then integrate it with respect to y afterwards. So that's called an iterated integral. And when we're integrating with respect to x, kind of like when we're differentiating with respect to x, we're going to treat y as if it was constant. Okay, so let's do the mechanics of this, and then the geometry of this is a little bit more interesting and would end up being a little bit more important for us to look at. The mechanics of this is that if we're integrating this with respect to x, what's the integral of x squared with respect to x? X cubed over 3. What's the integral of a constant, y squared, with respect to x? So y squared x. So the integral of 5 with respect to x would be 5x, right? So integral of y squared. And for this, a lot of times it's clear what you're working on, but just in case it's not clear, when you're putting the limits, make sure you include the variable just for your own sake, sanity. And continue to work this out. And here we're going to put the value of 2 in for x and no values for y yet, so y is just going to be left alone. So if we put a 2 in there, we're going to get 8/3 minus 2y squared, and then minus negative 8/3 plus 2y squared. Why am I writing so big? I'm writing big. So this is 2 times 8 is, well, 16/3? Minus 4y squared. So that's just the inside. And notice that it still has a y in it, right? So what this is saying is that this integral that we found is an area, right? When we do a single integral, it's an area. It's area under the curve. And so what we just found is an area, but that area that we found is dependent on y. And now, this integral sign out here is going to take this function, area function, and we're going to add up a whole bunch of area functions. And now if we integrate this with respect to y, I have 16/3 as a constant with respect to y. So this is equal to 16/3 y minus, and then I have that 4/3 business, y cubed. This time my y goes from minus 2 to 2. And then so you put in those values for y. 2, 32, 64. I think the answer is going to be 64/3 minus 16, 32. Is that right? Let's just say it's right. So this is my answer. And whenever you do a double integral, whenever you do any integral, right, if it's a definite integral, your answer is going to be a constant. It's just going to be a number. And that's why these things are technically called dummy variables, because it doesn't matter what they are, they're going to disappear, and you're just going to end up with a constant. So this would be the volume that we were seeing, you know, they were being approximated by those boxes. And so the exact volume is actually 32/3. Okay? So we'll see more geometry in the idea of an iterated integral, and then we'll get more fancy with different domains.